Welcome back to the chart table. I'm QMC Simpson, and today we're going to take the stars that we pre-calculated in the previous video, and we're going to do the strip forms and then plot them on a universal plotting sheet. So if you haven't seen the previous video, go back and watch that one so you can learn how to get the stars that you want based off your LHA. So we got the three stars right here and the DR latitude and longitude. The DR latitude and longitude will be the same for each star because you're going to end up triangulating to see how far away or on top, hopefully, of that DR you're going to be. Obviously, you need the date and time because you want to be in the right part of the nautical almanac. You do need a course in speed. Depending on how fast you get these lines of position, depending on how fast your ship is going, you're going to be a little bit farther away from your assumed position for that star. As you can see in my example, I started taking my star lines at 17, 16, 25. That's when I found Capella. So I wrote that down. Then we have Fomalhaut and Vega. You want to try to get your last star as close to the DR time as possible. So if you know your DR is going to be at 1730, be where Vega is going to be, on what side of the ship you're going to be, and have someone time it for you so you know exactly you have Vega and you say you got it. Just hold it until it says 1730. If it's a little bit past, like I have 5 seconds past, that's not a big deal at all. Everything in the nautical almanac is in GMT, so we have to convert our zone time to GMT. You just take your zone description and add it. We're in the Western Hemisphere, so it's adding. Yeah, I'm telling you right now, everything on this strip form is simple, easy math. You have some addition, some subtraction, and at the end here you have some multiplication. But as long as you get the right information here, you'll end up getting the ending result. So at that time, I got Capella on my sextant. My HS was 17 degrees. 53.3. The index correction. The index correction is based off the error that you have on your index arm for your sextant. You're using the same sextant for each star. You're going to have the same index error for each star. For this case, it is plus 1.1, and you just put that for all of them. So basically put the plus if it was off the arc, it was before 0. You'll subtract it if it's after 0 because you want to zero out your sextant. Dip is basically converting your height of eye. And it has a little table in the nautical almanac. You just know what your height of eye is. For this example, we use 10 feet. So you just go to that part of the nautical almanac, scroll on the dip table, scroll down until you see 10 feet, and then right next to it will be a number. It'll tell you whether to add it or subtract it. For our case, 10 feet is minus 3.1. All these are minutes. It'll be the same for all. All right. My HS for Fomalhaut, 23 degrees, 26.2. And in Vega, I got 42 degrees, 34.7. So to get your HA, all you have to do is take your HS, plus or minus your index correction, plus or minus your dip correction, and that'll be your apparent altitude. You just say 1753.3 plus 1.3, get 54.4, minus 3.1, and you get 17 degrees, 51.3. For Fahrenheit, you get 23 degrees, 24.2. And for Vega, you get 2 degrees, 32.7 minutes. All right. On that same page that you have the dip table, to the left of it, you'll see a stars and planet for altitude correction. You're going to take your HA and find it, whatever number it comes in between on that table. And then right to the right of that, you have a correction. So we took 17 degrees, 51.3, scrolled down that table till we found what this number goes in between. And right next to it was minus 3.0. From Fahrenheit, it was minus 2.2. And Vega was minus 1.1. With our answers, degrees, 48.3, 23 degrees, 22.0, and then 42 degrees, 31.6. Now we have our HOs. So basically this first part is correcting the site based off index correction and how high you are on the ship, correcting a parent altitude, HA, to get HO. Now this same process will be the same for local parent noon, because you take your zenith distance minus your HO, and then plus or minus your declination, but local parent noon is a different day. So we have HO. Now we have to find our assumed position, assumed latitude, assumed longitude, declination, and so on, to end up over here. So now we'll open up to the day in question, 09 December 2025, and we're going to look for hours. All right? The GHA of Aries, make sure you're using Aries, not the sun or the moon or the planets, Aries. The GHA in hours would be the same for each one because we have 22 hours on each star. For this case, it was 48 degrees, 53.7. Now the minutes are going to be a little bit different because we have 16:25 here, 25:15, 30:05, and so on. So we go back into the increments and corrections page, find the minutes table for 16, and we're going to go down until we see 25. Make sure you're getting Aries, not the sun. Sun is the first one. Right next to it is Aries. Aries would be the second column. When we did that, we got 4 degrees, 06.9. Go to the next minute one, 6 degrees, 19.8. And then 7 degrees, 32.5. Before we can get our total LHA of that star, you have to add another variable to it. For stars, we have this thing called a sidereal hour angle, SHA. That is always added unless it says otherwise in there as a negative number. So SHA, you get it from the same daily page. You'll see the list of stars, all 57 of them, and they'll have a SHA and a declination. We're doing SHA for right now. So the SHA of Capella was 280 degrees, 20.3. Fomalhaut, 15 degrees, 13.8. And then Vega had 80 degrees, 33.2. Basically, once you find the GHA of Aries, the star is not there. Adding the sidereal outer angle to it gives it the Aries calculation more information to get the actual GHA of the star. So this part, GHA of Aries, adding this will give you the GHA of the star. All right. We're going to fast forward this part for math purposes, but just know it's always adding. If you get above 360, subtract 360. Now we have the GHA of the star. We still need to get LHA of the star. So LHA is what we're going to go into the site reduction tables and use one of the variables to triangulate our square off to get all the other information over there. So none of them were above 360. Just cross them out. Now we're going to find our assumed position for longitude. To get that, all you're going to do is take the degrees from your DR longitude and just write them in. All right. For LHA, we want to get a whole degree of LHA. To get that, your minutes have to cancel out. So to cancel out these minutes, you just subtract those minutes. And it's subtracting because we are in the Western Hemisphere. Make sure you label it. All right, so 20.9 comes down here, making our assumed longitude 076 degrees, 20.9 west for Capella. For Fomalhaut, it's going to take the 27.3 from the GHA, 7.3, they cancel out. So LHA ended up being 257 degrees. For Fomalhaut, 354 degrees. Obviously, you take 70 minus 76, you get a negative number, add 360 to it, 354. Then we're going to take 59.4 down here. 136 minus 076, 60. So now we have the LHA of the star. This was the GHA of the star. LHA. Oh, I can't draw this. All right, now we have LHA. One of the three variables to square off in the site reduction table. The next one we need to get is the tabulated declination. That's number 2 out of 3 in the site reduction table. Right where you got SHA, I said this earlier, if you look a little bit to the right of it, right next to SHA for the stars, you see declination for the stars. You're going to take exactly what Capella, Fomalhaut, and Vega say and write them in. Make sure you label it north, because once we get down here, I'll explain why. Declination of Fomalhaut, 29 degrees, 29.2 degrees south. And Vega, 38 degrees, 48.5 north. Now, 21 through 23, that is if you had a correction to those. The stars' declination do not change that often. You can scroll through the daily pages to see how much they change, but they can keep their relative position really good. So from 21 to 23, I'm just going to cross it out because we don't need to do anything with it. Since there's no correction, 20 equals number 24. You just write it in. Now we have 2 out of the 3 variables to go into the site reduction table. We have LHA, and now we have declination. The last part is fairly easy, not real math, but possible rounding. It's asking for our assumed position for latitude. Now, when you look at our DR latitude, 36 degrees, 56.1. 56.1 is so close to 60, which is the next degree. I'm going to round that up to 37. And it'll be the same for all of them. Rounding to 37 will make a little bit less error when you go to plot these, and it'll look a little bit better too. Right here under 25, it has an S/C. S meaning same, C meaning contrary. And that tells you what part of the site reduction table book you would look in. On the left sides, you have sames. Contraries are on the right side. Now, when it's asking for the same or contrary, what is it talking about? It's talking about your declination and your assumed position latitude. Since these are both north, they are the same. You're going to use the left side of the book. Now, for Fomalhaut, our declination is south. Our assumed position latitude is north. They're going to be contrary. You're going to use the right side of the book. And the same thing for Vega. Both north, it'll be the same. And now we have the third part to go into the site reduction table. We have our LHA. We have our LHA. We have our declination, and we have our assumed position latitude. All right, that's the second part of the strip forms. It does look like a lot of numbers. Don't let that scare you. Just know it's simple addition, subtraction, and like I said, once we go over here to 27, 28, or excuse me, 29, multiplication. And if you have calculators, especially the scientific calculators, which are really nice, you'll be fine. Or unless you're just a math whiz and you can do it all in your head. All right, opening up the site reduction table. We're going to square it off. We're going to find at the top corners, you'll see LHAs. We're going to find 257. And once we have that, you'll see at the top, across the top and across the bottom, you see latitudes. You're going to find 37. And on each side of those tables going up and down, you'll see declination. We're going to use 46. These increments right here, we're going to get to those here in a second. But we're just going to use the whole degree for right now. Once we find that, you'll see that it says HC, a little d value, and a Z. So For this strip form purposes, HT, it's what's tabulated angle. Whatever the site reduction says for HC, we're going to write that for HT for right now. And then once we apply declination, we'll end up getting our HC. HT for Capella was 17 degrees, 56.7. For Fomalhaut, 23 degrees, 45.6. And last, Vega, 43, 15 even. Right next to that HC value was that little d. You're going to take that value, and it doesn't show positive or negative throughout the whole thing. It just has it on that first one. Whatever that first one is, it's going to be that one. For Capella, it said 34.4, and it was a positive value. For Fomalhaut, it was 59.7, and it was a negative value. And Vega was 18.4, positive value. All right, number 28, the capital F value, big F. That is basically taking your increments. For example, Capella, 1.4 minutes. You're going to divide that by 60. Okay? Divide that by 60. And do not clear out your calculator if you're using a calculator. But for the purpose of writing it on the strip form, just write it in there, round it up to the second digit. All right, that was Capella. 0.48. For Fomalhaut, and 0.80 for Vega. So I guess I lied. There's a little bit of division, but still simple math. And to get the total correction, number 29, you're going to multiply these together. For Capella, multiplying 34.4 by 0.02, we end up getting 0.68 minutes. Fomalhaut, we got minus 28.6 minutes. And then finally, Vega, we got plus 14.7 minutes. Right. With that total correction, all you're going to do is take the total correction and add it to your HT value, your tabulated altitude. With the HC for Capello, 17 degrees, 57.3 minutes. Fomalhaut, 23 degrees, 17.0 minutes. And Vega, 43 degrees, 0.3 minutes. All HC is taking HT and applying the rest of your declination. Because we found what it is for the whole degree of your declination when we went inside the book already. But there was always that added error. Not error, but you get the picture. I hope you get the picture. Now we have HC, computed altitude. Now we have to find, well, we don't have to find, we have HL already. All you have to do is take it from over here and just write exactly what it says over here. Once you wrote it in there, you have to find this little lowercase a value. The little lowercase a means intercept, how far towards the body you are, or how far away from the body you are based off your assumed position. So when you plot the assumed position for the star, you're going to have your azimuth or your bearing to that. And it's going to be how far closer you are to it or farther away you are. All right. Let's just do the simple math, and we'll talk about this more about the intercept. And all it is finding the differences between these two. So the differences between these two right here is 9.0 nautical miles. Next one, 5 nautical miles. And then you have 28.7 nautical miles. All right. Now there's two different things I want you to remember when you are trying to find out if you're away or towards. There's this saying, ho, mo, to, meaning if your HO is more, you are towards the body. Right? Then there's another one, CGA. I remember it by saying Coast Guard Academy, but it's basically saying if computed or HC is greater, it's away. These are phrases that you should have learned in A school. If not, you should be reading your publications such as Bowditch and Dutton's. And there's countless schools that we go to that mention this as well. All right, to find out away or towards for Capella, HC is greater, so it's going to be away. For Fomalhaut, HO is greater, it'll be towards. And for Vega, HC is greater, so it'll be away. Almost there. Almost getting ready to plot these. Also part of when you were in the site reduction table, like I said, it said HC, right next to it said little d, and right next to that was a Z value. That Z value is your azimuth, or which way it should be actually looking at when you're looking for this star. For Capella, it was 045.5 degrees true. All of them are true. For Fomalhaut, 174.3 degrees true. And for Vega, 069.5 degrees true. All right. To convert Z to Zn, kind of like with the azimuth of the sun video, if your LHA is greater than 180, Z equals Zn. If your LHA is less than 180, you take 360 minus Z, and that will equal your Zn. So our LHA for Capella is above 180, so Z equals Zn. For Fomalhaut, our LHA is 354, above 180, Z equals Zn. And then we got Vega, which our LHA is less than 180. We'll take 360 minus 069.5 degrees true, and that answer will equal Zn. And the answer we got was 290.5 degrees true. The information you need to go to your universal plotting sheet. I'm going to show you how to set up your universal plotting sheet, plot your DR. You're going to plot your assumed positions, so assumed longitude, assumed latitude. You're going to plot the bearing line. Then you're going to measure out your intercept in miles. In the latitude scale, you use that for miles, and how far close you are towards or away you are. And you just mark it and draw a perpendicular line through it. The perpendicular line is the line of position. The first one, the bearing line, that is your star line. You're converting the star line to a line of position. Now let's take this information and go to the universal plotting sheet. All right. Now we're at the chart table. Let's go ahead and plot these stars. So everything I had on the smartboard, I have in my strip form right here. We're going to transfer this information, or some of it for right now, to right here, which you see I already did. We got the DR position, our course and speed, Capella's assumed position, azimuth, and intercept. Same thing for Fomalhaut and Vega. There's a few pieces of equipment that you need, or tools. You'll need dividers, some type of slide ruler, or triangles if you prefer the triangles, and a pencil. I prefer a pencil over pen because if you make a mistake, you can easily erase it. Or if a star's line of position didn't come out as good as you want, you can just erase it and forget about that one. And hopefully you have at least two that intersect, or three. All right. Setting up your universal plotting sheet. As you can see, we have three lines right here and one latitude line. So this is going to be, it's going to look like a paper chart somewhat here in a second. So we have to get a couple more lines of longitude to put down, but we really don't have to do much with the latitude lines except labeling them. Okay. To get your other lines of longitude, you have to know what your assumed position for latitude is. Okay. As we know, for most of these, it's 37. So we're going to use 37. So you can use the compass rose right here. It goes from 0 all the way to 90. All you have to find is 37. So there's 35, 36, 37. Put a little dot. And same thing going down here. 35, 36, 37. And then you can take your slide ruler. Just line those up. Oops. Take your slide ruler, line those up. And then draw a line all the way down. Now you have your first one. Then you can just take your dividers, measure that distance between the two, and make it backwards and put little tick marks, maybe a little bit bigger, right here. Then do the same thing with this side, line them up. And draw a line. Now you have your three lines of longitude. The other way of doing it, which is most commonly used when you're using a universal plotting sheet, you're going to use this scale down here. Knowing your assumed latitude, 37, this scale on the side goes from 0 all the way to 70. It stops at 70 because, like, as the Earth rounds and it goes to the North Pole, and for example, and they touch, these lines right here get closer and closer and closer to where celestial navigation or plotting on a paper chart is not feasible. So it stops at 70. For right here, it has a little mark for 35, and we're about right in the middle right there with 37. So I'll mark 37 right there. Take my slide ruler, line up on this line right here for a straight line. Bring it down. And then measure that right there. Then you can just take your dividers, measure that entire thing, and then make your little tick marks, and then draw your lines like that. Also, this scale right here at the bottom, it goes from 0 to 59 with a section right here, which was the remainder of the 60 for 60 minutes, that breaks it down by 2. This is going to be what we do with our longitude. This is the longitude scale. So once we find our minutes and seconds for our longitude, we'll take this, like for example for Capella, the 20.9, we'll put the divider starting on 20 and then measure out 0.9, which ain't going to be much for this example. Then we take that and put it with the latitude, and you got that position. All right, before we start plotting, you got the label. We use 37 degrees for our assumed position for a majority of these, so 37 degrees north is going to be right in the middle. Increase going up to the North Pole, 38 degrees, and decreasing going down to the equator, 36 degrees north. We used 0.76 for everything, so this middle line of longitude will be 0.76 degrees west. Increases going west, 0.77 degrees west. Decreases going towards the prime meridian, 0.75 degrees west. Now that we have everything labeled, we can go ahead and plot our DR. So for our DR, I'm going to go ahead and do longitude first. I'm going to measure out 0.76, so I know I'm going to be somewhere over here on this side of 7.6. I'm going to measure out 19.1. For that, I'm going to put my point on 10, and we're going to use that line we drew, put it on 10, and get as close to 19 as possible. These go by 2, so 2, 4, 6, 8, and 19 will be right in the middle there. Okay, now we have longitude. We're going to find 56.136. Take your ruler and put it on a straight line. Scroll up to 56.1, which is about there. Then take your dividers and make a little dot. That little dot is your DR. And label it DR 1730. Now when we go to plot our star lines, converting them to lines of position, hopefully they're coming right on top of that DR right there. Now, in a normal world, you already have like a fix down here since we're going 0.45, and then you'll DR out, and so on. Once you hit that fix, you DR out again. It's a ever-revolving process. Okay? Let's go ahead and do the assumed positions, and then we'll get into the zeniths and then the intercepts. For Capella, the assumed position is 37 degrees, right on here, so all of them are going to be on this line right here. And we're going to measure 20.9. So put the point on 20, and about 0.9, about 21. Put it right in the middle here, and then put a little hash. And since the hash is a little bit light, I'll put a little dark in there. I put a C for Capella. Eventually, you can do it light because eventually you're going to erase that because you're not going to need it anymore. Our assumed position for Fomalhaut, 37. And we're going to measure 27.3. Put your point on 20. 2, 4, 6, about halfway. Put on your point. Make a little hash. Put an F for Fomalhaut. Lastly, we got Vega. 37 degrees. 59.4, so it's going to be really close to 7.7. Put it on 50. 59.4. Right there. Not quite on the line for 7.7. Put a V for Vega. Now you have assumed position starting out. Now, we've been moving. If you're not moored, anchored, or anchored by your keel, your ship is always moving. All right? We had a course and speed. Our course was 045, 18 knots. The time we got Capella was 17:16. Fomalhaut was 17:25. And Vega was right on the DR time of 17:30. Our time we want to get in the last star was 17:30. So we have to figure out how far we traveled going 045, 18 knots between these two right here. So the time we had between Capella and Vega was 14 minutes. So you're going to take 14 divided by 60. To get decimal hours. You get 0.22, you get 0.233, and just remember your D street triangle. So distance, speed times time. So time, we got 0.233 running threes. And that's hours. 18 knots. To get the distance between that time, you multiply them together. So times that by 18. We got about 4.1 nautical miles. I just did 4 nautical miles because it's very hard and very minute for 0.1 on this scale. So that's fine with me. And then we just take this, measure out right in the middle there, 4.5. Or you can use this compass ruler, as I just like using the ruler. Put the crosshair on the line, put the 4.5 right on the line. Then you're going to find Capella. And you're going to measure out 4 nautical miles. I'm going to move this because you want to get the scale as close as possible to the star. So you measure down. 4. Put the ruler back on it. And then you just put the point on the assumed position for Capella. And then make a little dot. So that little dot now is Capella. And then you can erase the old one. You don't need it anymore. Okay, now we have to do the same thing for Fomalhaut. Go ahead and do your little D street triangle. You're going to take the difference between 17:25 and 17:30, which is 5 minutes. You do 5 divided by 60 equals 0.08. That's time, so 0.08 hours times 18 knots. Times 18 knots. You get 1.5 nautical miles. All right. So I'm going to do this first. I'm going to measure out 1.5, which is almost the compass's closed length. Measure out 0.45, just like you did with Capella. Crosshair on the line, and then 4.5 right there. Slide it down to Fomalhaut, and then make your point. Doesn't move that much, but this scale was zoomed in a little bit more. You'll see it much better. That's your new Fomalhaut. Erase the old one because you don't need it anymore. Now Vega, we got right on top of the DR position, time. Vega will not move. It will stay right there. Okay. Now that we have the actual assumed positions for all of our star lines, our star fixes, we are going to go ahead and plot our bearings to that star. For Capella, it was 045. Right, so you measure 045. Crosshair, 45. Bring it down to Capella. And do a light line going through Capella. Okay. A light line because you will erase it later. We were 9 nautical miles away. So we measured 4-5 this way, so that's where the star is. We are 9 nautical miles away from the star. From that point we have for Capella, we're going to measure 9 miles backwards. All right, use the scale closest to Capella, measure out 9, and then put the point right on the assumed position and make your little hash right here. Now, to get the line of position for that, all you're going to do is take this 90 degree right here, put it on that zenith line. All right, measure it out and bring it down to that intercept. And then you can put your thicker line right there. That is your line of position for Capella. And go ahead and label her. Okay. Now, if all you got was Capella and you have a DR, wherever the DR intercepts, when you come down, put the 90 degrees on your line of position, bring it down to the DR, put a little point there, and put a square, because that would be an estimated position, right? Remember, estimated position is 2 or less lines of position, and you're trying to get a fix. That's why every line of position is one of the 6 rules of DR, because you get an estimated position with that, and you can DR off an estimated position. But we have 2 more stars to plot, so I'm not going to put the square. And how close it was, the square would have been to our DR. It would have been about, looking at this scale, about 2 nautical miles off. Not bad. But we'll go ahead and plot the star, other star. Fomalhaut. 074 degrees true, which is down here. Put the crosshair on. Crosshair is on the line. 074 up here. Move this over a little bit. Do that. Okay. Crosshair is on the line. This line is going on 074. Scroll over and do a faint line going through Fomalhaut. Okay. 074 is over here, so the star is right there. And we were going 5 nautical miles towards the body. So going 5 nautical miles this way. Measure out 5 nautical miles. Put it on Fomalhaut. And then do your little tick. Do your perpendicular line. Put the 90-degree line on the bearing. Bring this down to the tick you just did. And draw your thicker line. Make sure you label. Fomalhaut. Alright, so far so good. We got 2 stars plotted. The cross is about right there, a little bit off from our DR. Well, that's okay for now. We got one more star to do, and that is Vega. Vega's bearing 290. 290 is right here, so put the crosshair on the line. Line going through 290 right here. Bring it down to Vega. Do your faint line going through. And then your 90-degree line, your intercept. We are 29 degrees away from it. The star 290 is this way, so the star would be over here. Measure out 29 degrees or 29 miles. Boom. Put your point on Vega's assumed position, and we are away, so make your little tick mark right there. Then your 90-degree line perpendicular to your zenith, and bring it up to the hash mark and do your thicker line. And then label it Vega. Okay, now we have all three stars plotted. It didn't come out to a perfect pinwheel, a little tiny triangle right next to our DR. Now, this is when you can have the process of elimination, how good you think the fix is. Say you don't like how Fomalhaut came out. You can take it out, you have Vega and Capella. That cross would be basically right on top of our DR if you want to use that. I don't really do the process elimination unless the star was, the information I got for that star was totally off. I would put the fix right in the middle, right there. Draw your circle. And then obviously you can measure how far off you were. Put it right in the middle there. Put it right on top of Vega. About 2 nautical miles. Now, 2 nautical miles isn't anything. I would say that was a pretty good fix. If I were to give it a like an excellent, good, or poor, I would give it an excellent. That's pretty good. But if it was like all the way over here, that's over 10 nautical miles. Depending on the height of eye you are when you're taking these fixes, you're basically seeing anywhere between 10 nautical miles and 11 nautical miles for the horizon. If you can take that 11 nautical miles and draw a circle around your ship, if you're anywhere within that, you did pretty good. You might have to adjust your course over ground and all that to get back on track so you don't get further off track. The set and drift might be pushing you off a little bit, but that is a really good fix. Now, if you're getting into the 30s and 40 nautical miles off, something's wrong. You're probably shooting the wrong star. But if you do the pre-calculation right from the previous video and do this right, you can take this fix and you can do the manual input function into your ENL, your emerging navigation laptop, and then you can do the course and speed off of that. Okay, and then get ready for your next one. Do all your stuff on these or Stella, and then input that into the ENL. The ENL is basically, in the manual function, is like a computer version of a paper chart. You can make it the way you want to look at it. You can have the DR as much as you want, at least by the NavDorm standards, and you'll be good. So you'll most likely only get a star fix in the morning in morning twilight, nautical twilight, and afternoon nautical twilight. Because anything after when it's pitch black darkness outside, you're not going to see a crisp horizon. And more times out of not, a DR will be more accurate if you try to get a star. And then if it's a little lighter, you can kind of see the horizon. Maybe the moon's a full moon, you can see the horizon a little bit. You can possibly get it. and you can get the moon as well. And go ahead and give it a shot. If it comes over your DR, you can use it, and then you have an estimated position. But it won't happen all the time based off that horizon not being a crisp horizon. There are such things called false horizons, and you just got to take it with a grain of salt. There's nothing wrong with getting an estimated position in the middle of the ocean. I don't care who tells you that. Anytime you want to talk about not having a fix and it being a big deal is when you're in piloting or restricted waters, because you need to know where you are with that, especially with shoal water around you. But if you're in the middle of the ocean and you're taking star fixes and you are 2 nautical miles off, like in this example, that is a really good fix. If you're 30 plus, or excuse me, if you're 11 plus, you might want to reevaluate your fix and try again. Oh, one last thing, 6 rules of DR, right? You get your fix, measure out your course, 0.45, bring it down to your fix, make a course line. I always do a little arrow, don't have to. And then you can put your course and speed, 0.45 degrees true, 18 knots. You can do it there. I usually put it right here if I'm using this sheet for multiple lines of position or multiple fixes. And then you can just move on to the next sheet when you're ready to run. These sheets are awesome. There's 50 here, and I got it for like $10 on Amazon. You get it. There's a free version on Google. I can't remember the link, but there's a free version. It's just 11 by 8 instead of the square moldboard looking paper. But that is plotting your stars. If you like the video, give a thumbs up. If you need extra training, subscribe to the channel. If there's any training that you would like me to give, leave it in the comments. There's more videos going to be coming out with celestial, rules of the road, time, etc. So I hope you enjoy your time on the chart table. See you in the next video.